Okay, so we're going to look at Lisp, and I've already given you a tour of Lisp, and you've started on your implementation, so you understand Lisp to some degree there. And if we were to just look at programming in Lisp, that introduction I gave was probably enough for you to go to the Common Lisp manual and go and understand how Lisp works. Okay. So what's going to be different in what I'm going to talk about is that I'm going to actually talk about implementation. Okay. And the Lisp is actually a family of languages. Okay. It's old enough that it's branched off in various ways. And the reason for branching are many. Common Lisp is sort of, is full of features. And it's meant to be the language you would want to use to program it. Okay? Scheme is something that was created for teaching programming. Okay? And so there's many examples here. But something that's common to all of them are a bunch of concepts. Many of these concepts you've seen earlier, but it's interesting that these concepts got invented in 59 or so when Lisp was invented, and these were new concepts at that time. Okay? So, so like I said, many of these concepts you know. Some terms here you don't understand probably, like dynamic scoping. What does that mean? Higher order functions, homoiconicity. So those will be new to you, but what's familiar to you has come from, one can argue, from Lisp. Okay, the conditionals are done differently, but the fact that we have a conditional rather than a go-to statement is a big deal. Okay, and that was the contribution of Lisp. Okay, so that's why Lisp is good from a historical point of view. So, as I said, Lisp has many branches. We are not going to be implementing the practical language. That's not our goal. Our goal is to actually teach you about the fundamentals. Okay? We're not going to be focusing on Lisp as a programming language. So we're not going to focus on scheme. We want to focus on Lisp as a language that we will implement. Okay? And so the language we will implement, I'm just calling that PL Lisp to differentiate it from, so this is a Lisp that teaches you programming language design principles rather than how to program. Okay, the basics of programming. And it gets rid of certain details. Okay, you might have noticed already that our toString doesn't behave the same way as Common Lisp's toString behaves. And we'll see something called setQ that won't behave exactly as that too, just because Common Lisp has many ways of doing sets, and we're just going to have one or two. So it's going to sacrifice a lot of details. Okay, and it's going to have extra things. Okay, so it's going to have lazy evaluation and eager evaluation, which I don't think the other implementations do, just so that you understand what these two evaluations mean. Okay, and this PL Lisp that I'm going to present is based on the Lisp implementation you have. Okay, but it takes liberty with that. So, when Andrew and I were designing and Andrew was implementing that interpreter, we didn't quite know what we were doing because something like this hasn't been done before. So as I start discussing it, say, well, this is how it should have been, and maybe we will make it that way. The presentation is consistent with the implementation, but I don't want to change the implementation too much, because I'll break your code. So I'm just going to. So there's going to be. It's not exactly that. We'll be inspired by that. Okay. And all the concepts I showed you earlier will be in this implementation. Okay, that are fundamental to Lisp, conditional, and so forth, except storage management. And storage management has come a long way from when Lisp was invented. So, like I said, we'll hopefully have some section on garbage collection, that is state-of-the-art garbage collection, not state-of-the research. State-of-the-art is what Java does right now, or what C# does, and we have access to papers that go beyond that too. So I'll talk about that. I really would like to talk about that if we have time. Okay. So when I say Lisp, right, Lisp, I'll mean this Lisp that I'm talking about, which is something that is of our invention, not necessarily what the details of our. Some of the details are of our invention. So to make your project tractable, we've divided that into multiple assignments, and they're laid on top of each each other. So layering is good for implementation. I don't sort of have to go and say, hey, at the start of the semester, go implement Lisp, and then relax and say, okay, see me at the end of the semester. We're giving you incremental assignments. Can you see that this kind of layering or any layering does that conflict with teaching, or do you think that will promote teaching of some concept? The fact that you have layered implementation somewhere, when you're trying to teach something, will that conflict, or will that somehow help? So in each layer, the closely coupled concepts are presented together.
Yeah, that's a good idea.
And other reasons, I mean, that's anything you want to expand on that? That's, yeah.
Well, the pitfalls of it is if overall the student does not have a grasp on the basic foundation, that shaky foundation to the project will continue to impact them negatively as they continue on with the project.
So what you're saying is that, look, at the very bottom will be the basic foundations, then will be a little less basic and so forth. And by not just looking at it all together, you get to sort of focus on the basic and then the next and so forth. And almost any discussion of this will begin with, here's a function, here's how it works. We won't do that. Before we go to functions, we'll go to something simpler, okay? And hopefully that will consolidate, that will make it clear. And in general, okay, so have you guys seen the concept of layered systems and layered systems being presented incrementally in other courses you've taken? Say, compiler, how many of you done compilers? 2 or 3 students. So in compilers, was anything layered? Can you talk of some layers in a compiler?
Yeah, we had to do sort of a tokenization step before we could build a syntax tree, and then after we had the syntax tree, we could do some checking, and then we could build the actual representation.
Excellent. 4 layers. I actually showed 3. It's the scanning, context-free parsing, context-sensitive parsing, where you do the checking, simple table, and then the code generation. Right? Operating systems. No. Networking. Anybody done networking course? So networking is an area where people talk a lot about layering. And have you guys seen some layers in networking that you can name, just as Ben named the Ben?
Physical layer, transport layer, application layer.
Okay, so there's the ISO model, and then there's the model that works. These are not my words. I was a faculty member at Purdue, and one of my mentors there was a guy called Doug Comer, who's written many, many books on networking and who actually influenced the network. These are his words. So by the way, his license plate read TCP/IP. He was that much of a networking nerd. So there's 7 layers, or there are 3 layers, but there are layers there. Okay, that's the ISO layer, and he hated the ISO people. So they were Europeans, and he was an American, and the Europeans had written a lot of books on this stuff, and the Americans had actually built the internet. So that was his viewpoint. I'm just mouthing that. Operating systems. Do you divide operating systems? Do you just go and talk of everything, or do you talk of some? How do you partition operating systems? Ben again. Okay, so kernel versus user level is very good, but within the kernel, think of your assignments. You guys did some memory management assignments with Alok, and at least the ones with Don. There are some, did you create threads perhaps? So there's memory management, there's process management, there's process coordination, synchronization. So there's layering there too, and Doug Comer, actually the same person who's very famous for networking, built a system called Xenu that was meant for teaching operating systems. And what was very special about that operating system was that it was layered. Other operating systems like Unix were not layered. So he could go and do in a much smaller piece of code what Unix did in a much larger piece of code. And so his system that he developed for teaching actually, and writing a book, and that's a very famous book, it has been used in embedded processors a lot, because it was such a small footprint. Okay, so this idea of layering, layering is very difficult to get because you have to go and find the closely related concepts and say this is closely related. Any modularization is difficult. Okay, but we see the physical layer, the internetworking layer. That physical layer connects two computers together. Internetworking connects networks together, and then TCP/IP connects processes together, and UDP, whereas the other layers connect machines together. So that's one way to partition things. There's many ways to partition things. And compiler, scanner, parser, two kinds of parsers: context-free, context-sensitive. And OS, you have to have memory to create a process. Okay, so the memory management layer comes below the process management layer. You have to have processes before you can synchronize them. So all your semaphores and all come above process management. Okay, so you can have this idea is not new. Okay? So what was difficult for us was to figure out a way to go and define Lisp in layers. Okay? And so we do have something going, which we will use as a basis. Okay, and something going is basic functions in Lisp. That means these are functions that are implemented by the native language, and then functions that are defined in Lisp, and then we can go to eager and lazy evaluation after that. Okay? The server part is not adding any concept. I just copied and pasted and forgot to delete the fourth box. By the way, anybody who's done and is bored can take your Lisp interpreter right now. Based on what I've taught you about client and server, you can create a Java server client and a Java server and a Java Lisp interpreter server and a client, and even a Bash client, because if you just look at my code, you have to morph it very little to go make it that. So this is something you can do today. Okay, you don't have to know anything more about Lisp, and I think I've described the distributed IPC layer in enough detail for you to do the assignment. If you want to have concurrent clients, you'll need to go and use concurrency, and that you may or may not be familiar with, but lots of you have done concurrency before, and so you can even start that part. Otherwise, you can always have one client interacting with the server at one time, just as I did. Okay, so the server and client are not going to add any concepts to Lisp. Okay, that's kind of orthogonal. So, we are talking of sort of knowing the fundamentals of Lisp, okay? And starting off with the most fundamental thing. And the most fundamental thing I'm going to talk about is something called SExpressions that you don't even see in you don't need to, at least. Now, you probably don't see in any Lisp manual. Okay? But you really need to know about Lisp SExpressions to really know what's going on. Okay? So you guys have seen that in your assignment. You may not know why they're there, but you kind of know what they are. And I'm going to claim that a Lisp SExpression is like a Java object. Okay? And even if you don't know what a Java SExpression is, you've seen a Java object, and a Java object is an object that has the properties of a bunch of other data structures in Java. Okay? So it's a unifying. You can claim that if you had to teach Java, from an implementation point of view, you start with the class object. Okay? If you don't know what class object does, maybe you don't know what class list does, or what interface list does. Okay? So, as you might know, there are collections that are Java objects, and there are various kinds of collections. Okay? This kind of hierarchy came from Smalltalk, actually. And those are predefined for you by libraries. They're not predefined by the language. Okay? And then you can define your own, and then there are these classes that represent numbers. Okay? They are predefined. They are defined by the language, actually. So they are in java.lang. And then you can define your own objects that are subclasses or subtypes of objects. Okay? So a lot of data structures are united by class object. Okay? So if I was to again discuss Java, I would begin with class object. Now, are all data types Java objects? This is not meant to be a trick question. So, Mac?
No, they're primitive data types.
Sorry?
They're primitive data types.
Okay. They're primitives, and they're not united by anything. I mean, they're united conceptually by something, but not something physical that Java offers. Okay? So Java goes a big step in unifying. And by the way, there's many reasons for unifying. Reusability, understanding things. And learning something. If you have to go and you want languages that are easy to learn, and they're unifying concepts that you don't have to go and repeat, learn things again and again. Okay? So just as if you have some common user interface paradigm that applies to all your user interfaces, you don't have to learn things again and again. And that's something that Apple has tried to do. So that's a design choice Java took. That it had some things called Java objects and some things that were not Java objects. And I talked about synchronization. I talked about each Java object having queues. And it makes sense to not have every little int and double have two queues in it. Okay? And so, but you could have gone and made every data structure an object. And I've mentioned this language many times. And anybody remember or know a language in which everything? Firstly, before we go to that, a language in which there is no object-oriented language in which there is no Java, no object class. Anybody know such a language? Sorry? TypeScript? But TypeScript doesn't have class object, by the way? JavaScript. But it has objects, right? Okay. JavaScript. Any other language? Yeah. C#, I'm sure, has object. Okay, C# came out of Java. Basically, there was a lawsuit from Sun to Microsoft. So Microsoft, rather than towing Sun's line, decided to invent their own language. And so I think they took all the good points of Java and did something even better. They didn't make it portable. Okay? But the word C is a good one here. So the C++ decided not to have any unifying class object. So you could define all these classes, but there was no unifying class. Okay. And which is kind of surprising because C++ was derived from another language in which all data structures are objects. And anybody want to guess what that name is? C? C has no object. So C++ added objects to C. That's what the plus was. Python came after Java, actually, and after C++. And I think Python, Python is a lot like the language I want to talk about, which came earlier. But I think Python probably has some primitive types, no? Yeah, so I'm saying there's no primitive types. Everything is object.
Are you talking about Objective-C?
Which Objective-C? Yeah. That's an Apple, right? Yeah. So Objective-C actually and C++ came at the same time. And Objective-C might have had it because Apple embraced that, and that's why you know it, right? Because Apple still has that. That was like late 80s, okay, that Objective-C came around. So even that's a very dated language.
Sorry, Perl.
Perl has objects?
Perl 6 is all objects, Perl 5 has them, but not.
Sorry?
Perl 6 is entirely objects, Perl 5 has them, but not everything is an object.
So I don't know, it could be. It could be that they could make everything an object because scripting language you're not that concerned about efficiency. So Robert, I thought you would name another language. Okay, so the first language that really had a class object was Smalltalk, and it had everything. There was no primitive types. Small. Okay, so C++ tried to make Smalltalk practical, and it decided to get away with object. And Objective-C was a competitor to C++, and I've forgotten it because I can't remember anything interesting about it that I hadn't seen before. So it might have had class object, okay, except that it was C based. But the fact that it was Objective-C means it was extension of C. If it was extension of C, then you still have the C data structures. So I would argue that it didn't have, it could have had a class object, but not all data types would be object. That's guaranteed. Okay. So Smalltalk was great in that way. Okay. Not the most efficient thing, but great from the point of unifying. There's a lot of trade-offs in language design. So what does that have to do with SExpression? SExpressions are Smalltalk plus plus, if you will, in terms of unifying. So all data types are objects, But if you want to study small talk, if you want to study the foundations, you want to do something with it, you have to know about objects, of course, but you need to know about conditionals, which are not objects. Okay? You need to know about loops, which are something else, which are not objects. And loops and conditions are not united by anything else. You need to you need to know loops. You need to know about how to represent literals. Okay? Yes, internally there's an int, but how's that int specified, and what data type describes that? Okay? A double and string and constant literals. Okay? You need to learn about all of that stuff too. There's nothing unifying it. You need to know about variables. Okay? You need to know about method, class, and declarations. You need to know about enums, like things. Enums are just basically literals that are named by you. Okay? They're also values, they're not variables, but they were named by you or they have symbolic names. Okay? So you have to learn a whole lot of stuff that is not united with the class object. Okay? And Smalltalk was, Smalltalk 80 was the first version that sort of made it. So Smalltalk was invented around that time. And Lisp sort of went beyond Smalltalk in that sense and said, hey, we will not distinguish between data and code. Data and code will be unified by the same concept, and that concept happens to be SExpression. Okay? So we have this SExpression concept, and you can have various kinds of expressions. I've got these arrows which are like the is-a hierarchy in Smalltalk, but there's no inheritance in basic Lisp. There have been object-oriented versions of Lisp. Okay? But conceptually, SExpressions can be divided into atoms and compound SExpressions. Compounds can be lists or tuples, and lists themselves can be function declarations, function calls, programmer-defined constants, and just ordinary lists. Okay, so lists are a very powerful thing. Atoms can be literals, okay, or identifiers, symbols, and symbols can be function names, variable names, and that's it. Everything that I talked about is an SExpression that is stored in Lisp as an SExpression. Okay, so that's a foundational concept in Lisp. Okay, questions? We're going to expand on this a little later. So the fact that code and data are united has a name, okay, and you can break it up into two parts. Homo means same, and iconicity means representation. And how many of you have seen this term before? So this hand I expected to go up. Others should have also seen that. If you haven't seen that, you're not reading Piazza, you're not reading his posts. So Ben actually mentioned this term in one of his posts, and I said, this is not going to be totally unfamiliar. But it really means, in the context of Lisp, code is a list. Okay? And we see that function declarations are just lists. Function calls are lists. So in the terms of, in terms of Lisp, that's what it means. But we'll say that in general, if code is some data structure, and I say is in a loose way, that it is internally, a special form, or externally manifest, either way as inheritance, is some data structure type D, which means that it can be stored in variables typed as D, and all D operations can be invoked. Okay, so that's a powerful feature in Lisp, and so this is how an SExpression is different from class object. Okay, in purpose. Questions? We look at the implementation. So, as you've seen, I guess I used two terms, compound and composite. And Andrew and I actually wrestled with that. In the assignment, do I use compound or composite? Do you guys remember? Composite? Okay, good. Somewhere else later I go and say compound, I'll change that. So we'll talk of two kinds of SExpressions. Okay? And that's like the difference between primitive values and objects in Java, except that they are both united as SExpressions. And an atom SExpression just has a value slot, okay, and one slot. And a composite SExpression has two slots, not three, not four, not one, exactly two. Okay. So we can give these two slots names. The left one we'll call the head, and the next one, the other one we'll call tail. Okay. And as we see that a composite SExpression, the head and tail point to SExpressions. SExpression can be atom or composite. So I've got now a hierarchical, a recursive definition of SExpression, and so that builds, that lets me build complex SExpressions. Okay, and we can store the special value nil in a slot, and that nil will serve many purposes. It will be false value, it will be the null value in Java, it will be an empty list. Okay, it's an overloaded thing, but that's the basic idea. Okay. By the way, so I'm doing this implementation-based discussion. I did not implement the Lisp interpreter that Andrew did. I haven't even implemented your assignment. Okay, so expect me to make mistakes. Some of them might be deliberate, okay, but some of them may not be, maybe accidental. So please look at everything carefully and correct me when necessary. Okay. So this is stuff I added into your assignment. Nothing should be surprising here. And, so SExpression, I said, is the foundation for Lisp. It's the foundation for other things too. So one of my students that I'm working with did a job in New York with a company that's famous apparently, but whose name I can't remember. And they use SExpressions to store file data. Okay, so file data can be just unstructured text, or it can be some binary data. And to serialize data structures and deserialize data structures, they actually use SExpressions of that rather than JSON. Okay, so it's not again it's a concept that is still contemporary. And now Lisp is an interpretive language, which means that there's some other language that's being used as an implementation language, which I'll call a native language. Okay. So how the SExpressions are actually stored depends on the native language. Okay? So this whole idea of describing Lisp by its implementation is not a new one that I've invented. A lot of people describe Lisp using Lisp, which can't be quite used for teaching foundational thing, because if we don't know Lisp, we don't understand its implementation. Right? So I'll end our discussion with an implementation of Lisp in Lisp. But I assume that you know some object-oriented language, and we'll build on top of that. Okay? So if you build a Prolog interpreter for Lisp, it will be very similar to what you've done, except that the SExpressions will be stored as Prolog data structures. Okay? And those are easier to deal with than actually Java data structures. So I'm going to assume that the composite expressions and the atom expressions are objects in some language. In our implementation, they're Java. And we'll go and have methods defined on them. So when you have a composite SExpression, get head and get tail makes sense. And when you have an atom SExpression, get value makes sense. Okay? So I'll use these in our algorithms that I'll talk about later. Okay? Which mirrors what you have in the implementation. And it's important that, and we'll also have an is atom that will tell us if an SExpression is atom or not. Now, SExpression is an internal object. How we represent this, whether we call it get head, get tail, whether we have an is atom or not, is all up to us as an implementer. It's not something, the data structure is not directly visible to the user. Okay? Indirectly visible by writing Lisp, because the Lisp you write will access input SExpressions, but they are not something that, you won't be saying get head and get tail. And you won't be saying get value for sure. So that's important. Okay. Okay, used to implement this. Okay, questions? Okay, I haven't asked you guys a question. So I have a get head, get tails, get value. How come I don't have a set value and a set head, set tail? Chris?
Because the SExpression is what you're reading in, so there's no reason you shouldn't be really modifying it.
So you're saying we don't quite know what SExpressions are doing, but you think that what the user type gets converted into an SExpression, and you're not going to change what the user type changed. Great, great. So why have setters? As it turns out, the results are also SExpressions. All competition involves SExpressions. Andrew?
Didn't it say like with the list breakdown all objects are immutable?
Okay, so we want to make things immutable. Okay. Why do you want to do that? Is the next question. So why no setters? We want to make all data structures in Lisp immutable. And do you know in Java any data structure that's immutable? String. Anything else? String is something that you expect could be mutable but is immutable. Some things you expect to not be mutable and that are not mutable, that are immutable. Sorry? Files? I know, so that's how you could make certain things immutable, but what things are final classes? String is final class. And final class is not the same as immutable. Final class just means you can't subclass it. It doesn't mean that you can't modify objects of that class. Okay? String is a data type. What other data types are there in Java that are predefined?
I'm not sure if this exactly meets your definition, but once you define a normal array as a non-array list, you can't modify the structure of the array.
So that's very interesting. You know, what can't you modify? Can you modify the behavior of a class? That's the final keyword. Can you modify the structure? Can you add more elements? No, you can't do that in an array. But you guys are going too far, you know, from strings. Arrays are more complex than strings. What's something simpler than strings? Int or integer. Can you modify an integer? Can you make 5 behave as 6? You shouldn't have to, right? By the way, in Fortran, you could make 5 behave as 6. So all occurrences of 5 could become 6 if you did something. Okay? But in Java, a primitive value you can't change. If you got the number 5, you can't change. If you got a number 5 in an object, you can't change it. Okay? So, so a lot of things are immutable. And why do we make, so let's talk of string. String could be mutable. And you don't want to change 5 to 6, right? It will just confuse the hell out of you. But a string, why did Java choose to not make strings mutable? What do you gain by immutability? Wouldn't you have wanted an immutable assignment 1 with none of those corrections? Or maybe not, maybe you want changes. So, yeah, then?
Maybe constant size once it's defined. Like, once you define it, you can't change the size of the object that you modify.
So, the size of the object, which is kind of what Nick was hinting at. As it turns out, the object, so that we are getting anyway. Sizes of objects don't, so with lists and so forth, you have to reallocate the stuff. But that you'll get the structure. Here I'm saying the values can't be changed also. So yes, a string's size won't change. Indeed. So you don't have to go and put it somewhere else. You don't have to have a linked list or something like that to sort of make it go. Is there any other reason?
So immutable strings can be read very fast, but it's very slow to change it. So you need to index in the charts in a string.
So you're saying that reading and writing may have different costs in general for a collection, and reading is faster than writing. in both cases, you have to index to a particular character to read it, but in one case, you have to also go and add, change the value. So indeed, that's a cost you have to pay with any mutation. Anything that's going to be mutable. But there's something that you should get from having an immutable string, and I'm actually going to point to you. A long time ago, you asked me a question about deep copying and shallow copying. Was you, right? So it's always confusing. Are we sharing the pointer? When I say A is assigned B, am I assigning the pointer to A? Am I assigning a shallow copy, whatever that means? Am I assigning a deep copy? Now, can you relate that to immutability? Ben? So whether you copy shallow, deep, or assign pointers, it doesn't make a difference. The thing won't change. The only reason why program will behave differently when you copy is because if one copy changes and the other doesn't change, then the behavior is different. If you had a pointer, you would have both referring to the same value. So if something was immutable, you don't have to worry about this. So you can share objects much more efficiently. So we don't even have the discussion of whether we are doing a copying of pointers or not. It will always be, the pointers will be copied, the object will never be copied. Okay? And so it will be efficient in that. So that is why we have no setters. Okay? So they are immutable like Java strings and primitive values, int, and associated objects integer. Okay? And assignment, shallow, and deep copy of the same semantic. By the way, this is not the only reason for making strings immutable. In today's world, security is a big problem. And one way to break security is to go and take strings in your program and go and add stuff to them. If the strings are mutable, you can do that. So you typically take a string and add some code to it and execute that code. Okay, some programs may not check whether the strings are going beyond a certain length or not, and so that's the buffer overflow problem. If you have immutable strings, you can't change anything, so you can't go and play the string. Okay? So there are many reasons, but just one common reason is that we don't have to worry about copying costs. Okay. So we do need to have to supply initial values, and that if we are creating objects, we don't have setters, and we have the alternative, which we have constructors. But what we will do, and this is where I'm deviating from what Andrew did, for each of these particular SExpression types that we have, we'll have a separate factory. Okay? Factory gives us flexibility. And in your assignment, you were changing only the SExpression used for object used for composite. Okay? And so Andrew called it just expression factory. But we'll call it composite expression factory, what you've been calling, what we'll call meaning in my slides. And it'll have a new instance which returns an SExpression given a head and tail SExpression. Okay, and it'll underneath go and call a constructor with that. Okay, so we'll assume some factories to create that. And I'm also going to assume that there's a factory for all the atomic variations. Okay? Andrew doesn't have it right now, but this is something I can add to his code, or he can add without breaking your code. So we'll assume that, for instance, there's a new instance that takes the int value represented by the implementation language, like Java, and wraps an atomic object around it, okay, which is the integer SExpression. Okay, so the integer SExpression is something that is a subclass of atomic SExpression. Okay, so we'll assume these factories exist. Okay, for Java we'll assume another factory. Okay, and we can see that given how many of these types exist, it gets to be a pain to define these factories, and that's why Andrew didn't do it. But I don't have to go and list all of them. I can hand wave a little bit and say, yes, they exist for others also. Okay, so we understand now how to create SExpressions, how to read their values, okay, and we can't change them. we can build new SExpressions from existing SExpressions. Okay? So I can take an SExpression and provide that as an argument to my new instance method in a composite factory to get another SExpression that points to it. But I can't change the underlying data structure in it. Okay? I have two SExpressions that are sharing data structures. Okay? Questions? Okay, so let's start with the atom SExpression kinds. So we're going to divide our world into literals and identifiers or symbols. Okay? Literals are values. Identifiers and symbols are names for something else. We don't mean them literally. We're just giving them names. Okay? A function name, f, we mean something that f holds rather than f itself. Okay, so the true value in Java is an identifier that represents a literal. Okay, you can't make that a variable, but you can create a variable called t that holds a true value or any other kind of value. Okay, so we'll have our literals for the various types that we are used to. We'll talk of integer doubles and strings, and those are three primitive types that we do have in Java. And for Boolean, we'll have a literal called true, and then we'll have this literal called nil that is many things, including false. Okay. And like I said, then we also have identifiers and symbols, which are going to be a different type. Okay. So these are all atoms. So, is string really atomic? A string is a concatenation of characters, right? So, yet I call it atomic. And something is atomic, I mean, that way even an int, it's not really atomic, right? I can always break up the int into the bits there. So something is atomic or not atomic depends on whether you have operations to break up the number into smaller components. And we'll assume that a string is something you can't do char at. You can't go and say what is the third element of a string. Okay, you just have the initial value, it's a string, and there's no decomposition. Okay, so this is important. We are assuming that these slots hold values. These are not memory words. We are assuming that these slots hold values in the native data structures of the native language. Okay, so that data structure itself might be composite from the native language point of view. So from the point of view of Java, string is a composite object. Okay, but that as far as Lisp is concerned is one slot, and that is the string slot. Okay, and we'll never be able to go and say, give me the fifth character or the fourth character of a string, or even give me the length of a string. Okay, none of those operations are scaled. Okay, so that's just to show you the difference between the native language and the language variable. Okay. Okay. So now Java as native language, that's also kind of funny. Native language term is used in compilers. And typically, native language is a machine language into which you compile the native code. But since it's an interpreted language, we are saying that some other language is being used to interpret this language, and that language we'll call the native language. Okay? So Java is indeed the native language that way. Okay. So I think there's just a minute left, and enough noise there that we should stop. So we'll get to non-atomic SExpressions. And we said that, look, Lisp is basically a family of languages, and we are going to take liberties with Lisp. Okay, just because the idea here is to not so much teach you how to program in Lisp, but to help you appreciate what's in the language. Okay? So the Lisp version I'm referring to is PL Lisp, it's meant for teaching programming languages. And we've tried to base, and Andrew really has pushed me in that direction, to make it as consistent with Common Lisp as possible, so that you can actually test these things out in Common Lisp. And I'm going towards his side. That means there are some details that I don't like very much that we will put into this. But again, we will take liberties. For instance, we'll do lazy and eager evaluation, and we'll do some ML-like things in Lisp also. Okay, and we also talked about doing this in a layered fashion. And if you sort of think about something like an object-oriented language like Java, the class object is a fundamental base layer that you want to build on. Okay, and the Java class object is derived from Smalltalk object, which was even more unifying. It unified all data types, not just object types. I mean, everything was an object, including what you think of as primitive values in Java. All data types were objects, but not code constructs that had no relationship to class object. Okay, so what we see in Lisp is something. Lisp, of course, came before Smalltalk. Is something that's even more unifying. That something is the Lisp SExpression, and the usual data types, all usual suspects, are SExpressions, plus things that have to do with executing code, writing code that manipulates the data types. They're also SExpressions. So we said, and we saw that. I used the word compound here. So we've been using composite, right? So I have to change that compound to composite. So and a point I want to make here is that this. So we also saw that. So that meant that code is a data structure. Okay, in Lisp, code is a list, but in general, if code is a data structure, then we say it's homoiconic. The language is homoiconic. Okay? And homoiconicity is easier to is a smaller step in interpreted languages than in compiled languages. In compiled languages, a lot of the stuff that you write is thrown away by the time the program runs. Okay, so you don't have to remember what an identifier name at all. It gets translated into an address. You don't keep that information at runtime. In an interpreted language, there is no compile phase. So you enter an identifier, it has to enter the interpreter's data structure. It has to become an interpreted data structure. So why not make the interpreted data structure and the data structures you create be part of some unified concept? Okay, so that's why homoiconicity is more quote unquote natural in an interpreted language. Okay, but we will see that in Java especially, and that comes from Smalltalk, and this feature didn't exist in C++. We can indeed reason about things that were created at compile time. Okay, so there is some degree of homoiconicity in Java also. And we'll see that in a few slides, in fact. Okay. So what are SExpressions? Well, they take two forms. They can be atomic, in which case, and we'll define SExpressions as objects. Okay, we can define them in any way we want to. There's a whole concept of lambda calculus, which is all mathematical based, which is the basis for Lisp, and so we can work completely in terms of mathematical constructs. And like I said, if we were implementing Lisp in Prolog, we'll think in terms of Prolog data structures. But abstractly, we'll think of them as objects with operations on them. So an SExpression can be an atom or not. So that's an operation. That's an internal operation. And if it's an atom, you can access its value. And if it's not an atom, it has two slots or two properties in terms of Java beans: get head property and a tail property. Okay, and head and tail can both be SExpressions. So expressions can be atoms or composites. So we can recursively build this data structure. Okay, so you've seen this in your implementation. If you've started your implementation, you're somewhat of an expert in this idea. And then we saw one kind of surprising thing here, that there were no setters, there were only getters. Okay, so how do you create initial values? Well, you use a constructor or a factory. But once you've created a value, you can't change it. Okay, and that idea of making some data structure unchangeable or immutable is not peculiar to Lisp. It is something you see in a practical language like Java. We saw that the string data types is immutable, and we were a little confused about what immutability really means. Immutability is an adjective you can use to a class to say that you can't subclass it. That means the behavior of objects can't change. You can say the length of the object is immutable, so that's what happens in arrays. So you don't have to go and reallocate the data structure once if it's a dynamic data structure. But here we are saying that nothing changes about it. Okay, so the object's contents don't change in any way at all. Okay, that's what happens in a string. That's what happens in a string in Java, not what happens in a string in C or C++. And you've sort of accepted that fact that, look, some things are immutable, some are not. And if you step back, you want to know why things are not. What do we gain by losing flexibility? And one thing we gain many things. So one thing we gain is that we can share the data structure without copying it. Okay, so copying it and sharing a pointer to it has no difference. There's no difference if the data structure is immutable. Okay, and we're going to make all data structures in Lisp immutable, and that way we can just use pointers. Okay. So assignment, shallow, and deep copy have the same semantics with data structures that are immutable. So how do we actually create a data structure? And I said, look, we'll use factories, and that's not quite what happens in the current interpreter. The factory name is a little different for Composite SExpressions, and there are no factories for Atomic right now. But let's assume that we are working at a more conceptual level, that we have a new instance, and the reason to use a factory is that you get a level of indirection. And you've seen that in your assignment, that you can replace Andrew's basic expression or composite expression that he's got with your own SExpression. Okay? If you want to do this change, you have to go and tell other parts of the code, somehow have to access you have to somehow tell the factory that the change has occurred so that other parts of the code can get the right instance. Okay, so you have to have some way of telling the factory, use my class. And the way Andrew's done it, you can have factories that that return factories. That's the way I normally do it. But he's done it in a more simple way, that you just tell the factory what class to use, and the factory just instantiates the class to create the instance. Okay, and at least one student came to me and said, I don't understand what's going on in this funny getter that I'm supposed to return a value for, and that's understandable because you haven't seen this concept before. But what you have to tell the factory is that this is my class. So you have to somehow call a method in the factory saying this is my class. That means you have to go and pass to the method some object, some data type. So suddenly class, which is really a piece of code, it's also an object on which you can invoke class method or static methods, but it becomes, you also are trying to indicate a piece of code as a data type. So a class that you write at compile time, that which is compiled, the compiled version is an object in Java on which you can invoke methods. You can, for instance, say, tell me your methods. Tell me the signatures of the methods. Okay? So that is approaching homoiconicity. And what we are saying here with class and the generic parameter thing is that, look, what you want to do is set some class that is a subtype of composite. I should be consistent here, but a composite SExpression. Okay? So that's what this question mark extends composite expression is doing. It's saying not any old class, but make sure that that class happens to be something that is a subclass, a subtype of composite SExpression. Okay? So we can imagine this such a method for all factories. Okay? This is a method you have to invoke in your assignment. Okay? Questions about this? So like I said, not only is this a practical thing for our assignment, but we're also seeing this homoiconicity idea in Java. And if you get time, we'll look at reflection in more depth later. It's a very powerful concept. Okay, so this is towards Java code class, which is code is a object. Okay, compiled class code. So we said, okay, we have composite SExpressions and atom SExpressions, and to really understand Lisp, you have to go down and look at what forms all of each of these kinds take. So atoms are simpler. We can divide the world into literals and identifiers or symbols. Symbol is a term used in Lisp, and the usual suspects are in the literals. Okay. One thing that is not a usual suspect is a string. You don't think of string as atomic in Java, but in Lisp, you do think of it as atomic. Okay? So it might actually occupy multiple memory locations in Java, but from the slot point of view, there's only one slot allocated for a string in Lisp. Okay? And so we're talking of a native language. So Java is just one language you can use to implement Lisp. Any language that is used to implement another language is called a native language. When you're doing compilation, the native language happens to be machine language, or it could be assembly language, into which depending on how the compiler is written. But since here we are talking of an interpreter language, we're talking of using a high-level language, and so in our case it's Java. So that's why Java is a native language. Okay, questions? So this is where we left off. We have some understanding now of atom SExpressions. We don't quite know how identifiers are used. That's for later. But we know they exist. Okay. So let's talk now about composite. And as I said, composites have two slots that can point to other SExpressions. Okay. So we can build in general a tree, a binary tree this way. Okay. Now, Lisp stands for List Processing Language, so somehow lists are special. So a particular form of tree is special here, which is a tree that can be viewed essentially as a linked list. Okay? So in this linked list of element type E, and element type E can be any SExpression, we say that in the heads, so this is the structure we see here, that the head nodes are all the contents of the linked list items that you think of. Any linked list is a linked list of some nodes. Each node has got some data type, and it's got a pointer to the next node. So the tails are the pointers to the next nodes, and the heads are the contents of the node. Okay, that's the way you view this tree. Okay, so a linked list has to end at some point, and the linked list ends with the value nil in Lisp. Okay, the atom nil. Okay, which is not different from the Java value null. So we saw that a tree may or may not be a linked list. Okay? So lists are a special data structure. We also have tuples. So any composite expression that is not a list is a tuple. And what's a list? A little bit more formally, if you just take the rightmost path in the tree, then that rightmost path ends in nil. Okay, and if the rightmost path we denote as T1 to Tn, where Tn are the tails, then we can talk of Hi being a peer of Ti if they both happen to be in the same composite expression. And we'll say that the list is a list of elements Hi, where I goes from 1 to n minus 1. Okay? Because n is nil, so that is not really a member. Okay? So, questions on this? Okay, you guys have done the isList function. You know how to implement it. Those of you who've done it. So if a composite S is not a list, it is a tuple. Okay, so the rightmost path needn't end in nil, in which case it's a tuple. Okay. So why have lists? Again, we haven't programmed much in Lisp, and we won't be programming that much. We'll do some programming in Lisp. But lists take the role of arrays in C and Java. I say arrays because arrays are supported in the language. Lists are supported in the language. Array lists in Java are things you build on top of language types. Okay, so they are more like array the list type in Java because they're variable sized. But unlike Java, they're part of the language. Okay. So, for instance, you can have a point list, okay, as a list. So, what about point itself? That will be more like a tuple. Okay. Now, in Java, an object with a bunch of instance variables or properties is like a struct in C, and that's a finite number of elements and a fixed number of elements. And so here we are talking of tuples having only two components. Okay, and those components, tuples can have other tuples within them, so it's a nested structure, but at any level there's only two components. Okay, so if you're defining a point, x, y would be a tuple. Okay, questions? Okay, so so we will now add to an SExpression the isList operation. Okay, and we, that's, like I said, something you have to implement. So what does that have to do with a Lisp interpreter? Well, a Lisp interpreter is essentially a text representation of an input SExpression, and its job is to convert the text into an input SExpression and then evaluate the input SExpression to create an output SExpression, and then convert the output SExpression into some output text and give you back the output. That's its job. Okay, so this is how we are relating it to what you do with Lisp. Okay, as far as you're concerned, you type in some text, you get back some text. That's the interpreter. But internally, what's happening is that there is some parsing, and this parsing is given to you by Andrew, that converts the text string into an input SExpression. If it's not a legal input SExpression, Andrew's interpreter throws an exception. You've got to terminate the program and start it again. In Common Lisp, you've got to abort that particular. It's a little nicer. But that's basically what a Lisp interpreter is doing. Okay, so Lisp interpreter reads, does some stuff, etc., then does an eval, and then prints. So this read, eval, print loop is something that got invented in the context of Lisp, and it defines an interpreted language. Okay, like Lisp. Okay. So in the output, you should be able to get any SExpression, right? Because otherwise you're not using the full power of SExpressions. And I'm going to argue that in the input, based on what you've seen, the input SExpression has some limitations. And so what do you feel are the limitations? Or could be, what can you imagine, or what do you know, what can you derive? The input must include some operations. You're getting there, right? So plus 1, 2 is an input, and plus is an operation. Good. Somebody want to extend his definition? We haven't quite defined operation, but your intuition is right. Right? What else can you type? Can you type something that's doesn't have an operation and get back a result? It may be useless. What can you type? I see a nod here. Without an operation. I can enter plus 1, 2. What about just entering 1? As it turns out, you can. Okay, it may not seem very useful, but you can. Okay, so the input SExpression can be an atom. Okay, and we've seen it must be it must have an operation. You can type plus 1, 2. Can you type just within parentheses plus? It'll give you an error, right? So it's a function application. A function application, we haven't quite seen what that is, but can you think of a data type that represents a function application? So we have atoms, we have composite SExpressions. We know it can be an atom. And a function application would be not an atom. Okay. So if it's not an atom, is it one of the other two types? Is it a list or is it a tuple or both? From what you've seen of Lisp? So what does the function application have? It has an operation name plus what does it have? Arguments. So the function name and arguments together would form a what kind of data type? A list, not a subtle question. Okay, so at the outer level it can be a list, right? It can't be just a composite SExpression. It has to be a list because we're talking of a list of items here. And then I can say plus, and then plus 1, 2, and then again plus 1, 2 within nested. So I can have nested applications also. So I can have within the list sublists, which are all function applications, or I can have atoms somewhere there. So basically, I'm not allowed. So can you now say can you now define some restriction on input SExpressions? So we have a tree. It can be an atom or it can be a tree. And what's the qualification of the tree? Lists or nested lists. So no tuples inside. Okay, because it's all either function applications or it is atoms. Okay. So basically, an input SExpression does not contain tuples. Okay, so it can be an atom or it can be a list, and the list can have nested sublists in it, but we don't have nodes that are not lists or atoms. Okay, composite SExpressions that are not lists. But you can compute. I mean, we are talking of tuples, so you can compute them. So these function applications can create SExpressions that happen to be tuples. So now you see why it's called a list processing language, because the input is all lists. Okay? And then, of course, what you can create are tuples also. You can create lists, or you can create tuples, or you can create atoms. Okay? So the output, you can give it a list SExpression, and it can compute an atom. Okay? Or it can, of course, compute a tuple or another list. Okay, that makes some sense. Okay? When we go and evaluate lists, which right now, so all the examples you've given, have all had this feature. Okay, that you had to evaluate all these sublists, and the evaluation happens to have operations. Okay, so there's a notion of evaluating to compute an arbitrary SExpression. So that's interesting. The Lisp interpreter doesn't go and decide how to evaluate. The Lisp interpreter creates an input SExpression and then asks the input expression to evaluate itself. Very object-oriented. The object decides. Okay, so the semantics of what evaluate does is with the SExpression, input SExpression. Okay, so